And so today the first speaker is Henry Yuen from Columbia University. Go ahead, Henry.
All right, thanks, Ignacio. Hi, everyone. So this is a joint work with my student, Greg Rosenthal, who's on this call, I think. And yeah, so today I'll be talking about interactive proofs for performing truly quantum tasks, in this case, synthesizing quantum states and unitaries. And probably due to time, I won't have a chance to talk about synthesizing unitaries, but I'll just focus on the task of synthesizing quantum states. So let's get into it. So here's the motivating task that I want to think about. So suppose you're given a succinct description of an n-qubit quantum circuit C that has exponentially many gates. So I think a useful example to keep in mind is imagine that the circuit C implements, say, the time evolution of some local Hamiltonian for an exponential long amount of time. Okay, and your goal is to synthesize the final state of this circuit on input, say, the all zero state. So this is a very, very long circuit, and so we expect that the state psi that's the result of this circuit to be very complicated, and you want to get your hands on this state. So I call this task state synthesis. State synthesis in general refers to, you're given some succinct description of a state and you want to prepare the state. In this case, the obvious solution is, well, you can just run the circuit. You spend an exponential amount of time using a polynomial amount of space to construct the state. And we don't expect to be able to synthesize this state in polynomial time unless P space is contained in BQP, which we don't expect. This seems like a difficult task. But what if now you can interact with an all-powerful prover? Can you then somehow shortcut this long process to efficiently construct the state and have it in your hands? So here's the model that I want to consider. We have some quantum polynomial time verifier interacting with some all-powerful quantum prover. This interaction can be quantum. And we think of this prover as, it can do anything it likes. It can compute, very difficult problems, prepare difficult states. We just don't trust the prover. So the goal here is, by interacting with this untrusted prover, we want to verifiably synthesize this complicated state psi in polynomial time. So the question is can we do this? So let me be a little more precise by what we mean by an interactive protocol to synthesize a state. So I'm going to say that an interactive state synthesis protocol for the state psi is an interactive protocol that satisfies a completeness and soundness property. The completeness property is that there is some prover strategy called the honest prover strategy, such that the verifier will accept with some probability greater than C. So C is the completeness parameter. In this talk, you can think of C as being 1. So if the prover is being honest, it will always be accepted. And the output of the protocol, so the verifier is going to output some quantum state, and this output should be close to the desired target state psi. The soundness property is that for all prover strategies, no matter what the prover does, if the verifier accepts with some probability greater than S, so S is a soundness parameter, think of it as some number like, say, a half or 1% or something like that, then we want that the output state, conditioned on accepting, the verifier accepting, is going to be close to the target state. So if the verifier accepts, then it should have some good confidence that the state it has in its hands is really this target state psi. So that's what I mean by an interactive state synthesis protocol. Okay, so the goal is we want to construct such a protocol for the state psi. Now, maybe some of you might be wondering, well, how does this relate to a famous result about quantum interactive proof systems? There's this theorem QIP equals P space, which is by Jain, G, Upadhyay, and Watrous. Doesn't this imply that there's an interactive proof for solving this problem? After all, this state psi is the result of a quantum polynomial space computation that takes exponential time. But we also have this result by Watrous that quantum polynomial space is equal to classical polynomial space. So therefore, doesn't QIP equals P space imply something about our ability to solve the state synthesis task? Well, this starts to run into this distinction between quantum tasks and let's say classical computational tasks. Or another way to put it is really this is coming to the difference between search and decision problems in the quantum world. So the theorem QIP equals P space is a result about decision problems. The verifier in this setting, it wants to verify whether some input X is in some language L, and that's just a decision problem. It has a yes or no answer. State synthesis, on the other hand, can really be thought of as in some sense, a quantum search problem, right? At the end of the protocol, the verifier doesn't just want to have a yes or no answer, but it wants to have in its hands an entire n-qubit state. And the thing is, in the quantum setting, the relationship between search and decision problems is much more mysterious. So to give an example, in classical complexity theory, search problems and decision problems are often treated interchangeably, like they have the same complexity. So for example, if you have the ability to efficiently decide 3-SAT, then you can also use that to efficiently find satisfying assignments. But it's unknown whether this search to decision reduction extends to the quantum setting. So for example, it's unknown that, suppose that QMA were equal to BQP. We don't think this is true, but imagine that were the case. Does this imply that you can find ground states of local Hamiltonians in polynomial time? We don't know. At least I don't know of a way to do that. And in fact, I have some evidence in the form of an oracle result that kind of gives some evidence that there's no efficient search to decision reduction for QMA relative to the oracle. So at least in the case of QMA versus NP, there seems to be a difference between whether you can reduce search to decision. Now, coming back to our task of interactive state synthesis, if we think about the classical analog of this problem, I'll call this classical interactive state synthesis. This has a pretty straightforward solution. Again, sort of just using some kind of search to decision reduction. So here, let's say the goal is you're given a polynomial space classical Turing machine M, and you want to output the final state of this Turing machine after an exponentially many steps. And you want to get this final state in an interactive way, by interacting with the approver. So you can reduce to IP equals P space by simply just treating each bit of this final state S as the answer to a decision problem. For example, is the jth bit of this final state equal to 1 or not? And you can just summon for each of these output bits the IP equals P space protocol to determine what the right bit should be. So you can find the final state bit by bit. All right, so that's pretty straightforward. In contrast, this motivating task that we have at the beginning, this quantum state synthesis problem seems more difficult, right? So the verifier is trying to verify the construction of a very complicated, fragile object. It's complicated because to classically describe this object that it wants to get out at the end, the description involves 2 to the n complex amplitudes, right? And furthermore, you want this object in quantum form. And you want to ensure somehow that, for example, this state, n-qubit state that you have in your hands is not entangled with anything else. It's really has the right amplitudes and all the right phases. It's not quite clear a priori how one might try to do this. So the main result that we show is that, expressed in some kind of, in terms of what I call quantum state complexity classes, is that state P space is contained in state QIP. So state P space, think of it as the state complexity analog of P space, and state QIP is the state complexity analog of QIP. And let me unwrap, what this really means and give a little more detail about what this result is saying. So here's the theorem. Here, in order to kind of make this well defined, we actually have to talk about not just synthesizing a single state, but rather an infinite family of states. And that way we can meaningfully talk about asymptotics and complexity. So let's say you walk up with what I call a space uniform family of quantum states. Okay. So these states, psi n, are they're indexed by the integers. Psi n is a state on n qubits. For each n, there exists an interactive state synthesis protocol satisfying the completeness property such that where the honest prover is accepted with probability 1. And conditioned on on acceptance, which always happens, the output state is going to be exponentially close to the ideal target state psi n. Now the soundness property is if a prover is accepted with even slightly above exponentially small probability, then the output state conditioned on accepting is going to be inverse polynomial close to the target state psi n. That's the main theorem we prove about interactive state synthesis. Before I go on, are there any questions?
Henry, could you say a little bit about how you showed the decision to search hardness in the QMA? Maybe that could be a little illuminating.
Oh, yeah, so I won't be able to say too much about it. I mean, essentially, so basically the oracle just hides a random n-qubit state, like a Haar random n-qubit state. And the QMA oracle problem in that case is you want to distinguish between whether the oracle hides some state or it's just acts as the identity. So the witness in that case is going to be either the random state if that's what the oracle is hiding, or if that's the yes instance. And so intuitively, if you want to actually prepare this quantum state, you have to make an exponential number of queries to this quantum oracle. And having the ability to decide yes or no answers to the QMA questions, even though these are QMA oracle questions, intuitively doesn't help you locate or construct this state. So that's kind of the short summary of it. It's somewhat just not so satisfying because it's you have a quantum oracle and it's hiding a Haar random state, and there's no notion of locality. In some sense. So, it's not clear how much this is saying about like the local Hamiltonians problem, and the ability to prepare ground states, but it's at least some kind of evidence that it's hard.
Mm-hmm.
Okay, so actually, I should probably, I didn't explain what I meant by space uniform. You probably can guess, but let me sort of explain that. So, so let's talk a little bit about state complexity classes. So a family of quantum states, so you have an sequence of states, psi1, psi2, so on. We say that it's space uniform if there's a uniform family of quantum circuits, Cn, and these circuits can be exponentially large, but they are just restricted to using polynomial space. And each of these states in the family can be constructed from the circuit applied to the all zero state. So that's what I mean by space uniform. And it really just means that there's sort of like one quantum polynomial space Turing machine that generates each of these states. So state P space is defined to be, it's the class of all space uniform families of quantum states. And state QIP is going to be the class of all state families that admit interactive state synthesis protocols. And so since both of these classes are classes of state families, we can talk about inclusions and compare them with each other. And our main theorem, like I mentioned, is the inclusion that all space uniform families of quantum states admit interactive state synthesis protocols. So here, like I mentioned before, state P space and state QIP are what I call state complexity classes. We're talking about families of quantum states rather than families, than languages, which are just sets of strings. And here's kind of a more general question that I think is really interesting is, you can define all sorts of state complexity classes. And you can ask, well, what does the landscape of state complexity theory look like? And how does it relate to our typical complexity theory where we just talk about decision languages? All right, so in the last part of, the last 10 minutes or so, I'll sort of explain how we interactively synthesize a state. So here's the warm-up. We're first going to talk about an interactive state synthesis protocol where the verifier interacts with a trusted prover, in other words, an oracle. Scott Aronson showed a few years ago, or at least this is sort of the only reference that I could find, is that in this setting, there's a pretty easy way of synthesizing any quantum state. So there's a polynomial size quantum circuit V, such that for all n qubit states psi, there's a classical oracle A that depends on the state psi, such that the quantum circuit makes a polynomial number of queries to the oracle, and it can synthesize psi up to exponentially small error. How does this protocol work? Well, the basic idea is that the algorithm V is going to build the state psi qubit by qubit, and it's going to use the classical oracle at each step to compute something called conditional amplitudes of psi in superposition. What are conditional amplitudes? Well, the easiest way is to describe it kind of recursively. So let's say you take your state psi, this target state. I'm going to write it as the following. So I'm going to pull out the first qubit and write it in this way. So alpha 0 and alpha 1 are complex numbers. Psi 0 and psi 1 are going to be n minus 1 qubit states. So you can think of psi 0 as being the state of the the n-1 qubits conditioned on the first qubit being 0. And similarly, psi1 is the state, the residual state conditioned on the first qubit being 1. And then you can sort of recurse on psi0 and psi1 to compute these other complex numbers. So, you know, for, let's say B is equal to 0, then alpha 0, 0 and alpha 1, 1 are defined in analogous ways. And you can sort of continue splitting off these states in this way. And these complex numbers that you get out are conditional amplitudes. Another way of thinking about it is that if you multiply the conditional amplitudes together, then you recover the amplitudes of the original state psi. All right, so here's the protocol. The verifier is going to ask the oracle to compute the first two conditional amplitudes. So these are the alpha 0 and alpha 1 that we saw earlier. Since the oracle is trusted, the verifier knows that these numbers are really what they're supposed to be. The verifier is going to prepare a 1 qubit state. So it's going to be alpha 0, ket 0 plus alpha 1, ket 1. It has this 1 qubit, and then it's going to uncompute these conditional amplitudes, alpha 0 and alpha 1. So it'll just perform the reverse of the oracle call. Now, controlled on this 1 qubit state, controlled on it being in some classical basis state B, the verifier is going to recursively invoke the same protocol, but for the smaller n-1 qubit states. So it's then going to construct in superposition, you know, conditioned on the first qubit being 0, it's then going to construct psi 0, and then conditioned on 1, it's going to construct psi 1. And by definition, if it does this successfully, then it's really going to construct psi. Right, so,
Henry?
Yeah.
The question in the chat by Abhinav Deshpande, he's asking, to understand the state classes better, would state QMA be the set of accepting witnesses for a QMA computation?
Oh, that's a good, so I actually haven't thought of how you define state QMA, but that seems like a very reasonable definition, yeah.
And,
right.
And I have a question about what you're saying right now. So in general, this action that the prover does of telling you like the amplitudes after, you know, sort of setting a prefix to what the first part of state, that should be something that is outside of QMA, right? Because otherwise you would have the decision to search. Search a decision.
Yeah, I mean, well, I guess again, QMA refers to decision problems.
Right. I guess.
Yeah, I guess it's kind of related to what Sandy was mentioning yesterday. I guess you can, yeah. But I guess, yeah, the moral is that computing these amplitudes seems to be more difficult than QMA in any sense that one could consider. Okay. Yeah.
Okay, good.
Yeah. Or it's not clear how to do it in QMA. Yeah, so you know, so this is the protocol with the trusted prover, and if you unroll this recursion, you know what you see is that the queries that the verifier is making to the oracle is really just to get these conditional amplitudes. All right, so cool. So you know, our goal is to remove this trusted trust assumption, and so the intermediate result is. Well, we know something special about the states that we want to synthesize. They come from a space uniform family. It turns out that the conditional amplitudes of states from space uniform families are actually computable, at least within some small exponential error. It's computable in P space, classical P space. There's a polynomial space classical Turing machine that on input n and given a particular conditional amplitude to compute, it will compute it for you. So that gives us an idea. Well, let's take this protocol with a trusted prover, and instead of trusting it, why don't we replace this part right? With an interactive protocol to compute these conditional amplitudes. So here, let's leverage the fact that QIP is equal to P space to ensure that we actually get these conditional amplitudes correctly. Right?
Henry, sorry, there's another question, couple questions actually about the uncompute. People are confused how this happens.
In the trusted protocol?
Yeah, this step through the verifier uncomputes alpha 0, alpha 1.
Yeah, so here, the Oracle call is just a classical Oracle call. So there's, so all of this is happening coherently. So conditioned on the prefix of the state, it's going to send the prefix to the Oracle, and the Oracle will return in a separate register. It will XOR the conditional amplitudes in the, it's just like the standard model of calling an Oracle in quantum algorithms. And this uncompute is just to perform the inverse of that. And in this case, I guess you can just call the Oracle again, and it will just undo the XOR of the conditional amplitudes, and you've erased the classical information about the amplitudes. So in the trusted Oracle setting, this is pretty straightforward. That's not so tricky. It gets trickier when we have an untrusted Oracle or untrusted prover. Right, so we have this idea to compute these conditional amplitudes, let's run the QIP equals P space protocol. And hopefully everything should work out. Right, so this is the attempt. We replace this first step with running QIP equals P space to compute alpha 0, alpha 1. We do everything as before. In the uncomputation step, one might imagine that let's try to run the QIP equals P space protocol in reverse. All right, so there's some problems with this. And the problem is that since the prover is untrusted, it can be adversarial, and it knows we're trying to compute these amplitudes, and knows that we're trying to construct a state. So it might try to adversarially perform some quantum attacks on the protocol and get us to accept and generate a state that's different from our target state. What we've done, now that we have this QIP equals P space protocol embedded inside our state synthesis protocol, the soundness of this implies that the prover can never get the verifier to accept wrong conditional amplitude. So at least classically, the alpha 0 and alpha 1 will be correct, right? Because that's what QIP equals P space guarantees us. And so in some sense, I'll say that this QIP equals P space defends against classical attacks. But a malicious prover can, at least in this protocol as described, can cheat by mounting quantum attacks. So what's an example of a quantum attack? It can perform something called an entanglement attack. So for example, during the QIP equals P space portion of the protocol, which is just sending, let's say, classical messages back and forth between the verifier and the prover can entangle its private workspace with the messages. And at the end of the protocol, the final state of the verifier and prover could look like the following. The verifier's workspace could at least look like what it's supposed to. If psi is alpha x ket x, then the verifier's workspace could look like this, but then the x part could be entangled with the prover's workspace. I mean, after all, the prover is getting what prefix we're conditioning on to compute the conditional amplitudes. So it knows what x is. And this would be bad because when the verifier outputs this register, this is actually going to decohere, and you're going to get just a probabilistic mixture of x's, and it won't be coherent. So that's bad. There's sort of kind of like a subtler version of the entanglement attack. Maybe the prover isn't entangled, but it could introduce spurious phases which ruin your state. So I see in the remaining 0 minutes I have, I'll just quickly say that we can fix these problems by introducing genuinely quantum, we can introduce quantum tests to detect these types of attacks. And roughly the idea is that the verifier is going to maintain the invariant as it's building the state qubit by qubit. It's actually going to have two copies of the state. So, at the jth step, we assume that as long as the verifier hasn't rejected so far, it's going to have two copies of this intermediate state psi j. Okay, and it's going to try to at each round, it's either going to grow the state by 1 qubit, or it's going to perform a test round. And the prover won't know until it's too late whether it's a test round or a grow round. If it's a grow round, then it'll do what it did before. It'll run the QIP equals p-space protocol to grow it by one, this first copy by 1 qubit. But if it's a test round, then it'll run QIP equals p-space, but then it won't actually introduce an extra qubit. It'll just try to perform the reverse. And if the prover is being malicious, then this state could get corrupted. But what the verifier is going to do is it's going to perform a swap test between these two copies. So we're assuming that this second copy is the true, like a legitimate valid state. So it can test these two copies. And if the test passes, what the verifier can deduce is that the prover actually didn't do anything fishy in the QIP equals p-space portion of the protocol. Okay. Which means that in the grow step, actually, you go from j to j plus 1 in the correct fashion. And once that happens, then the verifier will just ask the prover to give it a second copy of the j plus first state, and it'll do another swap test to make sure that they're the same. And regardless of whether we're doing a test round or a grow round, we maintain the invariant that we have two copies of the correct intermediate state. Okay, so I'm out of time, but maybe I'll just quickly mention that I think the most interesting part of this work is that there's just a ton of interesting open problems to think about. So we showed that state p-space is contained in state QIP, but we don't actually know how to prove the reverse. It'd be really nice if we can show that state p-space is equal to state QIP, but we don't know if that's true. So that's an open question. Are there cryptographic applications of interactive state synthesis? Is sort of an elaboration on that, like it'd be really cool if there was like an interesting notion of zero knowledge state synthesis. Like what would that mean, and can we achieve that? What kinds of states can we construct with multiple provers? Presumably we can construct more complicated types of states. And then, finally, more generally, what does what does quantum state complexity theory look like? Okay, so I'll stop here. Oops. And, unfortunately, I didn't get a chance to talk about unitary synthesis, but I would be happy to talk about that offline. Thank you.
Okay, thank you very much, Henry. So we have time for questions now.
Can I ask a question, Henry? Yeah, a couple of things. I didn't quite follow your test and generic protocol. And then I had a question on the previous slide. Oh yeah, what's the what's an upper bound? Do you have an upper bound on the this inclusion that you gave that you aren't sure is tight?
Oh, an upper bound on state QIP?
Yeah.
Whether there's any upper bound at all, yeah.
Is that NX or X?
It's not 100% clear to me because you might try to brute force over all prover strategies, and it's not obvious off the top of my head whether there's any there's any dimension upper bound on the optimal quantum prover strategy. And I should mention that actually, even proving QIP equals p-space, the decision version, I think the hard part was, again, showing an upper bound on QIP. Like eventually they showed that there's an STP that characterizes it, but I'm not sure if there's an obvious upper bound.
Perhaps a basic question I could ask is, what is the power required for the honest prover? Do they have to be in just p-space? The protocol you stated?
Oh, for the honest prover, yeah, p-space, because they have to be able to compute conditional amplitudes.
And p-space and not sharp-p.
Right, that's because these are space uniform states, so they can encode p-space complete problems.
And what if they were sharp-p uniform?
If they were sharp-p uniform, I think it still might be p-space because we're using, they have to compute these sum checks for, oh, I see. I'm not 100% sure. I think it still might be p-space because they have to solve the sum check protocol, right? So oh, but I guess, yeah, actually then it might be sharp P, yeah.
I guess my question then is state QIP contained in the class where you talk to a trusted p-space prover, or like have a p-space oracle? And would that help with your first question? So using the fact that maybe it's easier to bound just a BQP machine that has access to a p-space oracle. Maybe that's something that's easier to bound.
So what's the model? Like there's no completeness and soundness anymore, right? Oh, so in that model, I mean, I guess, what Scott showed is that actually all states can be constructed in that model, right? Mm-hmm. So even, uncomputable states, whatever that means. Yeah, so that one contains everything as far as state complexity goes.
So, Henry, can I ask a question?
Mm-hmm.
So it seems that, okay, this protocol only works when you have a pure state, right? So can you say something about mixed states?
Oh yeah, that's a great question. I don't know. I mean, I thought about, maybe you can try to construct like a purification, but it's not clear. Like suppose that you had a space uniform family of mixed states. Does that imply that the purifications are space uniform? That's like totally not clear to me.
Yeah. Hey, Henry, do you know what the status of the classical analog of this question is? You're trying to construct a probability distribution.
Oh, that one is, right. So that one is, okay, so classical distribution p-space is contained in classical distribution IP. For the reverse direction, you mean like an upper bound on the IP, like constructing like sampling from a distribution. I'm not sure. Yeah, I imagine the upper bound would also be p-space, but I haven't thought about it.
Sorry, can I quickly ask you, you have this test and grow protocol. So I was a little bit unclear about, I think I missed something about it. So, so are you assuming that the prover sort of gives you SciJ on demand, and then you check whether the next, and then you do checks on it in terms of whether it grew properly, and then swapping, are those the two tests? Is that the way to think about it?
Roughly, yeah. So in the test round, we don't actually grow the first state, but instead we just run QIP equals P space forwards and then backwards, and we test whether these two states are the same. We're assuming this, like, but sort of by induction, that the second state is honest. In the grow round, we do grow this state by 1 qubit. And then we just discard this second copy and ask the prover for SciJ plus 1.
Sorry, so how do you get the inductive, since you're asking for this state, what gives you the guarantee that it was correct to begin with?
Oh, I see. Because of the test round, if that passes with high probability, then we know that in the grow round, this first register state is grown correctly.
Right, but if you already know that, why do you need the second copy then?
Oh, because in the next step, we're going to again do a test or grow, and you need the second copy to ensure that the test round has the right guarantees. So again, like what's happening in the test round, we're not actually going to grow the state. We're just going to we're going to make the prover think we're growing. So we're going to pretend we're growing this first register, but we're not. But we just want to make sure that the prover hasn't done anything malicious to the first copy. So that's why we need, inductively, why we need this second copy to test it against.
And the swap test, does it tell you that you're in some symmetric subspace, or what does it eventually, what do you eventually get from it?
In general, yeah, that's what the swap test promises you. But since we have this invariant or this inductive assumption that the state of these two registers it's a tensor product of pure states, then the swap test will really ensure that we really have two copies of the same pure state.
Okay, so any other question? So there is one in the F&A. Is the preprint version of this available online?
Oh yeah, so this should come on the archive hopefully soon. Yeah, so this will be out soon.
Okay, so we have 1 minute left. So do you want to say something first about the synthesizing unitaries?
Oh yeah, so this, I'll mention one thing. Okay, so what is the task of synthesizing unitaries? Here you're given a description of an exponentially long circuit, but then you're also given an input state in quantum form. So you only get one copy of it, or maybe a small number of copies depending on what model you consider. And you so call that input state phi. You want to synthesize the circuit C applied to phi. So it seems very similar, but now the difference is you no longer, as the verifier, no longer has even an implicit classical description of the output state. And you want to generate this output state. And the question is, can you do it interactively? And this seems very much more difficult. And we kind of have we don't have a similar result like this one. What we can show is that if your unitary has an assumption on it, which is that it acts non-trivially on a subspace of only polynomial dimension, right? So out of 2 to the n dimensions, it only acts non-trivial on a subspace of dimension poly n, then we can actually do this unitary synthesis, solve this unitary synthesis problem. But how do you go beyond polynomial dimension? That's an open question. So.
Okay, great. Well, thanks a lot, Henry.
Yeah, thank you.
So next speaker is Andrea Coladangelo from UC